Let's look at this case when we take correlated samples such that one sample is always similar to the previous sample. So for example, a sequence of speech or audio samples. So usually we don't have very high frequencies there, and that means that the curve through the samples is more or less smooth. So now we will take the dimension n equals to 2, and we will obtain a two-dimensional vector space of samples, which could look like this. So we are taking these blocks with two samples each, yeah, and then if our signal, for example, is a sequence with these numbers, we will get the following sequence of variables. So we're vectors. We are having blocks of two samples each. So this is what we have. To take a look in a more practical way, let's go through a Python example. So in this Python example, we're going to use a lib-rosa to load our audio files, matplotlib to plot, IPython display to listen to our signals, and numpy for mathematical operations. Here is our signal processing parameters. So we are using a sampling frequency of 32 kilohertz, and we're defining a time vector of 1 second that we're going to use to plot our signals. So the first signal we are going to use is the classic The Number of the Beast introduction from Iron Maiden. So I'm loading using a lib-rosa, then we're normalizing. I want to have the signals from -1 to 1. Then we're plotting here so we can see this is what it looks like, and let's listen to it. So now what we're going to do is to plot the two-dimensional vectors with their sample values of even indices on the x-axis and their odd indices on the y-axis. So we have pairs plotted as a plus sign. So what we're doing, we're taking even and odd indices of our signal. So this is what we're doing here. And now we have two-dimensional vectors, and we can see that they have this very interesting shape here in this diagonal. So this is the same signal, but we're plotting in a two-dimensional space. Yeah? So since the odd and the even values are similar to each other, we get a distribution of vector points near the diagonal of the space. So we need to sample this space only near the diagonal. So more generally speaking, we should sample more densely near this diagonal. This shows that we need fewer reconstructions values or fewer code words as when compared to the one-dimensional case, which means fewer indices for them and fewer bits for the quantized signal. So in vector encoder, we're dividing our signal into signal vectors. We find the nearest code word and we transmit its index to the decoder. On the decoder, we read out the code vector from the code book using the index from the encoder. We concatenate the sequence of code vectors into a sample string. So a very interesting property is that vector quantizers not only give an advantage for signals with memory, but also for signals without memory. In the scalar case, we can sample an any dimensional space on a regular grid, which is given by the coordinate axis of this space. Whereas with vector quantization, we can use something like a dense sphere packing into this any dimensional space, such that we reduce the distance between reconstruction vectors, the so-called code words, and we reduce the expectation of the quantization error in this case.